And he'll be telling us about some very nice work he's done on causality violation and so on, or conditions for and so on. So,
okay, thank you. So generally, giving the talk in the are always very difficult, and easy meaning you have to speak very less, and second is I always have a sleepless night before giving talk. But yesterday I have in my trouble I slept too much. Anyway, so basic point. So the talk is on causality constraint on the QFTs. So first, the causality is a Lorentzian concept, and it is quite useful in constraining many effective field theories. For example, in the high derivative gravity case, recently using causality, the high derivative terms were constrained in a recent paper by Maldacena and collaborators. So, causality is a useful tool in order to diagnose if it's a good theory or it's a bad theory. So, the basic point of the causality that we are going to take is that if I have two operators, say A and B, this should be zero outside the light cone. So this would be our causality criteria. If A and B is outside the light cone, then the commutator should be just zero. So the first question that we will ask is that although causality is a Lorentzian criteria, how can I understand how is it encoded in the Euclidean quantum field theory or Euclidean quantum field theory? In Euclidean quantum field theory, we don't talk about causality, but we know some work by Swinger, Whiteman, Osterwald, and Schroeder that every good Euclidean quantum field theory is in one-to-one correspondence with every good Lorentzian quantum field theory. So, by good, I mean there are some properties that one has to satisfy. Good Lorentzian has to satisfy unitarity. Number two, Poincare covariance or invariance. And three, causality. Whereas for Euclidean theory, the corresponding properties are Euclidean invariance. Number two, we have permutation symmetry. Then I have reflection positivity. So here, more or less people know all the terms. Causality I have explained. So Euclidean invariance is just Poincare with all the metric are +1 or -1. Just a rotation in the plane. Permutation symmetry is suppose I have a correlator with operator inserted at say x1, x2, x3, x4. Then it doesn't matter if I write down in terms of correlator. So suppose I have correlation function of this would be same as x2, x1 dot. So
for a bosonic
so we will not be talking about harmonic operator in our. So all will be considered bosonic operator. For harmonic operator, maybe there are some minus signs, but we know how they are related.
All the operators have to be the same.
Need not be. I mean, like it's just the position. It just you need just these are the positions. So theta of x1, say basic point is that you can just write down. So you can just write down this as say this 2-point function. The same as psi of x2, theta of x2. I'll come back to this a little bit.
I guess we're just using. I see, but I'm also confused. For n, here of course just because of translational invariance, maybe it just depends on x1 minus x2. But in general, will it be true for n-point function if you have, the operators are different and you have to change them? It is still the same?
The basic reason is that, basic point is that if you have Lorentzian, thing, then there is a time order product that something is suppose so either you define time order or anti-time order or more complicated time ordering. But in Euclidean, everything is like space-like separated, so you can always rotate one point to other. I mean, there is no time ordering basically. That's the point.
What if this like an operator, a third operator sitting at x3 which is very close to x2?
Yeah.
Then this psi prime and theta psi prime OP will be very different. I mean, why should they be the same? The 2 3-point functions.
Yeah.
Sorry?
Suppose you have 3 different kinds of operators. Now, operator A comes very close to B, and both of them are very far from C. Shouldn't that be different from A comes very close to C and very far
those
from
two will be 2 different channels. So for example,
that's what they're asking.
so say I have psi, say theta. So I bring psi together and theta together. The operator that run in between will be different compared to the operator if I bring psi theta and if I bring psi theta together. But nevertheless, by this principle, you will have, if you include all the exact sum, this will be the same. So this is the conformal bootstrap. The basic principle is that it doesn't matter because you can always interchange.
But what you're saying, so really, let me ask you, the value of this Green's function, when psi and theta are very close together, shouldn't it be different from when psi and psi are?
So you have to sit at a point where both of them are like. So if you have an OP, so okay. Suppose you have operator here, so say 0, 3, 1 somewhere. This OP is valid up to this. This OP will be valid up to this, unless you hit the singularity. So if you are sitting at a common point where both the OP channel converges, or both have good OP, expansion, then you can relate this. I can set the same value of GG bar and compute them, and I'll get the same value. Basically, their expansion will be different. Their expansion parameter will be different.
So it's one. Sorry, but let me just understand. It's one thing to say that okay, we have O1 at x1, O2 at x2, O3 at x3, etc. And then you can compute this by doing first one OP and then the other and so on. And if you are in some region where all of them are converging with it. But it's another thing to say, okay, this is some Green's correlation function. You compute it whichever way you want, as long as it's legitimate. But its value when O1 and O2 are very close together is the same as the value of the Green's function when O1 and O3 come very close together. That's a different statement, right? That's a statement of a function of many variables having the same value when two are coming close together, regardless of which two come close together. Do you know what I'm saying?
Suppose I hand you over exact 3-point function. It's up to me where I want to expand, right? Expansion will give me the same result. Suppose I give you the exact answer for the 3-point function, and then I do a series expansion around say x1 to x2, or in the other case x2 to x3. I'll get because I started with the same answer. So maybe I do not.
I'm just saying, okay, let's take a 3-point function. O1 at x1, O2 at x2, O3 at x3. Right? Why should this equal O1 at x1, O3 at x2, O2 at x3?
No, I'm not changing the position.
That's what was confusing us, because when you wrote G x2, x1.
So this is G psi of x2.
Okay.
Not psi of x1.
Okay, that's what he means. I'm sorry. I think we were all a little confused. What he means is, by that he means x2 always labels the operator O2 in his notation.
Yeah.
Sorry about this, I was confused. I didn't see a second line. So okay, now I understand.
Okay.
This
So
is just to say that it doesn't matter where you put that operator in the chain.
Yeah, but this will be important. This is an important distinction between Euclidean and Lorentzian QFT. Because in the Lorentzian QFT, these two may not be the same because there is a time ordering which will prevent them to be the same. We will see.
Yeah.
So,
okay, I got you.
okay, so this is in general. So the point was that good Lorentzian QFT is one-to-one correspondence with good Euclidean QFT, and the way we are going to use is through the correlation function. There may be other quantities that we can find out, but we are going to approach through the correlation function. So in the Euclidean case, I'm going to. So reflection positivity is the following statement that it basically is greater than 0. Two state greater than 0. For example, suppose you have psi, sin, theta, beta, 4-point functions. Then, if you want same state, suppose you take the OP channel where these two come close and these two come close. Then sin theta, you have to choose some reflection reflection symmetric points where you insert your operators. This can be written as this. So this is a state which will demand that.
What is the definition of inner product? This is we are doing conformal field.
Yeah.
Okay. So there's some definition of the inner product in the usual way that you insert one operator at minus infinity or at the south pole.
Yeah.
Are you going to define that a little bit or no?
A little later. I'll come back to this reflection positivity a little later. Yeah.
Why is the presence of null states unphysical?
Which state?
Null state, you are demanding the inner product to be greater than zero.
Yeah.
Equality, what problem would equality work?
No problem with equality cause.
Null states will decouple from the spectrum totally.
For example,
since Shiraz is here now, let's unless of course you should answer. He was just saying that reflection positivity, which you define more carefully, will turn out to be a statement of inner product being greater than 0 in a CFT. The question asked was, what about null states? Are you going to discount it? Probably they just decouple, right, or something. Right?
Yeah, I mean, the usual rules of Hilbert spaces, they're all non-zero states are positive.
Yeah, so it will just decouple, I think.
And okay, so there's a decouple, so no more discussion with that. But the point is that what we are going to do, we can always take the non-null state, and the constant that we are going to get is using positivity. So, okay, since Siran is here, let me recap once more. So the point I just emphasized till now was that good Lorentzian QFT is one-to-one correspondence with good Euclidean CFT, provided in the Lorentzian, it's not QFT, so not CFT, just QFT. Provided in the Lorentzian QFT, I have like unitarity, Poincare symmetry, and causality. And in the Euclidean theory, I have Euclidean invariance, permutation, symmetry, and reflection positivity. So the question that we started with was that causality is a Lorentzian criteria, but in the Euclidean case, there is no causality. So how is causality encoded in the Euclidean theory? So this is the question that we want to answer to start with. Okay, so let me start with the correlation function. So first property of the correlation function in the Euclidean QFT is that this is single value. It has only singularity at the coincident points of the two operators. Otherwise, it is single value. And so number one property, it is single value. Number 2, it is permutation invariant, as we have just. So this implies that x1, x2 dot 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 same as g x2, x1 dot dot. Okay. Now we'll take a case of 2-point function, and we'll see how this works. So let's consider a CFT for simplicity. Although this discussion are general for QFT, but we consider CFT for just for here for the discussion, and consider 2 operators of scaling dimension delta, and consider so this is given by delta can be integer, non-integer, anything, but you see that because everything is positive here in the Euclidean case, it is a single value. It is single value, and now how do I go to the Minkowski? So how do I go to the Minkowski case? All we have to do is that in the complex t-plane, we have to do an analytic continuation from Euclidean time to the Minkowski time, and you see that at the end what we are going to get is that t square plus y2 square minus 2 delta, because at the end this tau 2 goes to I3. And clearly you see that it has a branch cut, because it can be positive and it can also be negative, so it has a branch cut.
What are the 2 integers space and time?
Sorry? Yeah. So I just, it can be in any time, so I just separate them, I just put them in the, for simplicity, in 2 levels. So let me, the place of the branch cut say here. So how I go from Euclidean to Minkowski? So that will determine if I have this, or I have a phase factor exponential I pi delta times
You will assume that it's unit.
No, sir. You're only continuing. I thought depending on whether you continue upward or downward, you get a plus I epsilon or minus I epsilon, therefore time ordered or anti-time ordered.
Exactly. So if you do that algebra, and write, basically you can write it as a log, and then if you do that algebra, you will get a factor of this factor extra, because there is a I epsilon and there is a minus I epsilon. You will get a relative factor of I pi delta. So as Sandeep just said, I'll choose a convention, because in the Euclidean it doesn't matter if I put it here or here. By permutation symmetry, in the Euclidean this is same as theta of tau 2 y2 theta of 0 0. But in the Minkowski, we see that depending on the path, I have 2 different choices. And let me choose my operator ordering. I'll say this is time ordered. So, and I'll assume tau 2 to be greater than 0. So this I'll say is same as t2 y2 theta 0 0. And this path is going to give me theta 0 0 y2.
Are you assuming unitarity here? No. So it's 1.5.
I mean, maybe there is some, but I don't require anything over the delta.
What gave you these orderings?
Sorry?
What told you that this one is t and 0 and the other one is 0 and t?
I declare that if I don't have to do anything, that will be time order. That's my declaration. And if I have to do something, some multiply with the phase, I'll get it as the anti-time order. Sorry?
If you cross the branch,
Yeah.
that will come from there.
Yeah.
Okay, what?
So this is my definition that.
Okay, I can give you the first one.
Yeah.
But then the second one should be non-arbitrary given the first one, right?
Yeah.
Why does that relation hold that if you cross the branch gate you have to get the other time ordering? See, you can declare that if I don't cross the branch gate, that's time ordered. But then, are you independently declaring that if you do cross the branch gate, you get the other time ordering?
So,
or does it imply?
So my so here it is simple because here I have only 2 point function, so it has to be the other. But the thing that I'm saying is that if you don't cross the branch guard, operator. And suppose you start with this, and suppose you cross a branch guard, then it will be let me see, it will be on the branch guard that you cross, that will be on the left. I mean the branch guard, the operator, branch guard of the operator that you cross, that will be on the left. Suppose this is my definition. So this is what I'm going to follow as a definition.
I mean, the point is that the jump across the branch card is well defined, right? Because if you, for example, if you have a log,
yeah,
then when you change the sign of the log, that it picks up an ipy or whatever, that is well defined. So once you choose the value on top of the card, then the value at the bottom is fixed because that jump is fixed. I think that's what he's saying.
Yeah.
So he's making the value at the top to be time ordered. How does that fix the value at the bottom to be anti-time ordered?
No, because the jump is fixed. So once he's fixing the value at the top, then the jump is fixed because it's a log function that gives you the value. I think.
So the statement here that the jump is fixed to be the commutator.
So the jump is fixed by algebra. It's what it is. It's because going from one side or the other is like taking plus I epsilon or minus I epsilon.
Yeah.
You see, because going from one side is going through this way is equivalent to saying just stay a little bit away from the branch this way or a little bit that way. And we know that one guy is time order, the other guy is anti-time. So that's just equivalent ways of saying.
Yeah. So one way of doing it is through the irrational prescription, which is equivalent as just said. But we are going to draw paths because that will be much more intuitive. For example, this variable will become g, and this you can write down as actually if g is equal to t minus iy and z bar is equal to t plus iy. So what it will happen is that if you want to go from one to other, all you have to do is to rotate g to exponential 2pi. So this will be, and g will play the role of the conformal cross ratio. You can arrive at the same just by using irrational prescription. I can show you details later. But the basic point is, you see, I started with single valued thing in the Euclidean correlator, but in a Minkowski, it's no longer single valued. So depending on the path, I have two choices. And clearly, if I want to compute commutator, I can just subtract these two and get the commutator. So this is as I said, one of the criteria of commutator causality is to compute commutator if it is so commutator of A and B may be non-zero inside a light cone. So although in the Euclidean I cannot see causality directly this thing, but if I appropriately continue to the Minkowski, I can compute the commutator and find out whether this is zero or non-zero. Okay. So this will be the basic building block of the talk, that how I see from the Euclidean the causality. Okay.
What did you say about commutators again?
Yeah, so commutator, if I have A and B to be space-like separated, commutator is zero. So basically is permutation variance. Euclidean case always space-like separated, so I can always order as the way I like. But in the time-like, suppose these are time-like separated, then I cannot. I can have a non-trivial commutator. Then I have to bother about the ordering, and this is the way I am getting the ordering. And and ordering is important only in the Minkowski. So causality. Sorry, I am saying too many good words, but this is what I wanted to say. Yeah.
And within 2-point functions, it's obvious that the causality criterion is being satisfied. Yeah. Just because your first singularity occurs on.
Yeah, that's right.
With 3 or 4 point functions.
Yeah, it's maybe not correct.
Sorry. So, okay, you gave us a way of continuing from Euclidean to Minkowski.
Yeah.
Okay, and there is a way to continue, I have to understand it for n-point correlator, but let's say...
I'll give you an example of 4-point function.
Yeah, which will give us the time-ordered, say, 4-point function in Minkowski space, right? Okay,
Yeah.
so far I understood. Then what did you say about commutators? That is, okay, go ahead. Now you're interested in the commutator, so yeah, go ahead and say what you said.
Sorry. Yeah. What did I say about the commutator?
I mean, so you explained what time ordering is, if you like what anti-time ordering is.
Yeah.
And then go ahead.
Yeah. So suppose I want to compute the commutator. So the way to compute commutator is just subtract time ordering from anti-time ordering. That will give me the commutator, and that will just pick up the
there is, you want to compute, say, an equal time commutator? I mean, these two operators are at whatever time they are.
Yeah.
Okay. Yes, fine. Okay, so is the difference between going around this way versus that way?
Yeah.
So you're saying that jump across the thing will give you the value of the commutator.
Yeah.
Okay.
And within 2-point functions, that singularity is started at t equals y. So the only jump occurs when you go across the card. So that's t greater than y. So you have the causality criterion.
Yeah.
Obvious.
Yeah.
That things can only have non-trivial commutator. It's like separate.
Otherwise, you don't hit the card.
Yeah. I don't
You
think
just go.
Now I understand your comment. Okay, fine.
Okay.
Thank you.
So, in this way of thinking about computing commutator as a diagnosis of causality, let me go to the 4-point function, and we will start see that 4-point function is totally different from, more interesting than 2-point function. Okay, so let's consider this 4-point function. In the Euclidean case, I can put wherever we want because all of our space is separated. But let's consider a particular situation where I put only, say, x1 is equal to 0, 0, 0, x2 is equal to down to y2 0, 0, 0, x3 0, 1, x4 0, 0 is equal to 0, 0. Suppose this is the way I put it. So, if I draw suppose I want to continue from Euclidean to Minkowski, where this tau2 is say time like compare. I want to go to a position where this tau2 will be time like compared to this, or whatever combination I want. So I get so many choices in the. Starting from one value of correlation function, I'll get many choices depending on how do I analytically function. So, depending on the rules, I'll just draw the diagrams. Here and somewhere very at infinity. So I'm analytically continuing the this space. So this one is at O1, this is O3, and somewhere at infinity O4. Okay. And suppose I want to.
This is in the x and y some axis, or what is this?
So this is complex tau plane.
Complex tau.
Complex. So suppose I start with this. And clearly, so this is the real time.
So it's actually had x1 is all zeros.
Yeah,
O1 should be origin. O1 is not at the origin.
Okay, so I shifted my coordinate.
Okay. And x2 is separated in x2 you can't get drawn. Huh?
Yeah.
Okay, you draw x2.
Yeah. Suppose I want to reach here. So let me draw the branch cards. So the paths that I have.
Sorry, I'm not understanding this diagram. What x3 had a 1. What was that 1? That 1 was space or time?
This is space.
Space. So why? So you're only drawing time.
Yeah, only drawing.
Thank you.
So suppose I want to go here.
Only drawing tau. But literally x1 and x3 seem to have the same value of tau, right? 0.
Yeah.
Okay, so then
No, so these are the branch cards, the points. Where do I see the singlet? So let me draw.
oh, for each one you have tau, but one is 0, 0, 0, the other is 0, 1. So accordingly, the branch cut will appear at tau square equal to 1.
Yeah.
Now I'm with you. Okay. Okay.
So suppose I want to reach here. So what are the paths? For example, I just go here like this. So this is tau 2. I want to. So here tau 2 is time more than. Here tau 2 is time more than all the things. So this will give me time order. So this will give me theta 1, theta 3, theta 4.
So since you're drawing everything on the complex tau plane,
Yeah.
you shouldn't even be telling us where tau is. Right? Tau is just a variable. You should just be telling us the spatial location.
That's right.
So all 3 of these operators at spatial location 0, and 2 is special because it's at spatial location.
Y2.
No. So 1 is at spatial location 0, 2 is at y2, 3 is at 1, and 4 is at 3. Now, and now you're going to be moving the tau to location of x2.
Yeah.
Which was at y2.
Yeah. Sorry.
Yes.
Some compost.
When you say the branch cut is located somewhere, that I mean, if it were a 2-pointer, I understood that. What does it mean here, just to understand?
So
it's a function only of tau. Sorry, what I said last was wrong. The other 3 guys are just set to be tau equals 0. So we know the spatial locations of all guys and the time locations of 3 guys. So this whole thing is now a function of one complex time, which is the complex time of the operator theta t. And we're drawing the branch cuts of this correlation function on that plane.
okay. So these are the branch cards. Sorry. Yeah.
Oh, that. But how do I decide?
Where is the branch card?
Yeah.
So let's see this picture.
Okay.
So suppose this is the time. So this is at infinity. Suppose this is O2, this is O1, O3, and O4. Set to infinity. So somewhere here. So clearly, if it hits here,
On the x-axis is real time, right? Or what is
no. This is the real space-time.
real space.
Yeah.
Okay.
Y and tau thing. So this is T.
Okay, that's t. Okay.
So where are the branch cards? So if theta 2 hits this is branch card. Then basically, this is the light cone.
Light cone from there. Okay.
Yeah, so I can compute where is the branch card. So this will be this point. If it hits here, that will be the branch card here. And infinity somewhere here. So I can go and maybe it will hit here somewhere.
But that light cone, just to understand, is a function of tau and y, right?
Yeah, I can solve tau in terms of y.
And
This is for example tau is equal to y.
but there it's in the complex tau thing. Right?
Yeah.
Sorry. So what you're saying, where does the branch cut originate? I mean, I'm still having a little trouble translating.
So theta, the location of the theta 1 is y.
Yeah. And this will be y minus 1 or y plus 1 or y minus 1.
What's y?
Y is the location of x2. Yeah, y.
Okay. Y2. But then that's all. Okay, yeah. Because the cut is totally manufactured,
Yes.
right?
Yeah.
You're just telling us where it originates.
Yeah.
Okay. Then I'm good.
So suppose I want to go somewhere here in the tau plane. such that somewhere here, in just schematic in the sense that I want to reach a point where tau 2 is greater than, I mean like tau 2 is always, tau 2 is in the, say, somewhere here, suppose I want to reach. Or suppose I want to reach somewhere where it is time like separated compared to say theta 2 and theta 3, say for example. Sorry, theta 1 and theta 3, which will be like somewhere here. Then I have
which will be above.
Yeah.
Above theta 1.
Yeah. Okay. So how do I? So this is the simplest part. This will give me time order.
And when you say time order, what is the ordering exactly? Which one is?
So highest time will be at the left.
Highest time on the left. Okay.
Okay. So there is a second path I can choose is this. There is a third path I can choose this. There is a fourth most interesting path where I can choose here. So maybe it becomes a little messy, but so if I am crossing from the right, so theta 2 is crossing theta 3. So what I have to do is theta 3 made to the left of theta 2. Sorry. Theta 3, theta 2, theta 1, theta.
This is for which part?
This is for this part. That's where you just cross one of the branch cuts of theta 3. So basic rule was as in the
each crossing involves
just each crossing involves energy.
But it's operator 2, right? So if you are just going to cross theta 3, then
why was the top one? The top one was just a simple path?
Yeah.
Wasn't that theta 2, theta 3, theta 1?
Because theta 1, these are all space-like separated. So that was
commute.
Yeah, so like
yes, right, because time order.
Okay, I see. And then now I understand this. Okay, fine.
Okay. Let me cross this path. So here I am just crossing only one branch cut compared to theta 1. Then I have theta 1, theta 3, theta 2, theta 4. Sorry. But the most interesting part comes from here.
So which is that? That was the one that crossed the theta 1 branch cut?
Just the theta 1 branch cut.
So 2 and 1 are interchanged and the rest of 2 are brings over. Okay. One with the rest is.
But the most important, so these are just follows from the 2-point function. No difference compared to 2-point function. Okay. So if you have followed 2-point function, then this part, this should be very, very clear. But the most interesting part, which comes in the 4-point function, is this part. Why this is interesting? Because this is crossing 2 branch cuts, one and the second, and this was not present in the case of 2-point function. Why is this interesting? Interesting because this is a complex function. This 4-point function is a complex function, and it is not guaranteed that if I cross one of the branch cuts, second branch cut is going to stay at the place where it is. So it can move around.
Is it possible to give us a simple example of a function with 2 branch cuts like this?
Okay, I'll give it, but I'll try, but that will be wrong. Very so
the log of log or something.
Yeah. So maybe g minus 1, g minus 1, say for example.
So this is one branch cut, and now you're going to take another square root.
So no, the point is that suppose I rotate g around 1. Second branch cut, I don't need to go. If I cross this, point is that already this is going to shift or not. That's the basic question. So if I have a branch cut here, I just rotate it. So I get g minus, say I rotate g minus 1 to g minus 1 to the power exponential 2 pi. So it will go as I pi g minus 1. So it becomes
the location of the branch cut.
Yeah.
That seems pretty general. Right?
Yeah.
So if we take log of this function, for instance, that would be an analog of your kind.
Yeah, exactly.
Or square root, that's not.
This 1, 3, and 4 are in the equal time. Okay, but why are you calling it time ordering?
Oh, so time ordering meaning whatever is the highest time would be at the left, and this time ordering doesn't matter. I can always write theta 3, theta 1, theta 4 interchange. It doesn't matter because these are space-like separated.
But even in the second case, also you are considering also this. Okay, like the 1, 3, and 4 in the same time.
Sorry.
Even in the second case, okay, in the third case, 1, 3, and 4 are at the same time side, right? So then,
no, but if you cross, you get a branch cut because there is a branch cut. If you cross, you pick up the phase factor. That's why this is different. Just like a 2-point function.
Okay, I think you are doing something like you are trying to separate out the. Okay.
You see, more what you should be looking at this is basically I'm giving name to the operation that I'm doing. So operation, if I go here without crossing any branch cut, I'll call it as a time order. If I go like this, I cross one branch cut, then I'll call one of the operator gate switch. So this is the way I'm giving my definition. These two are different because there is a phase factor which differs in these two cases.
Yeah, that's fine. Okay. Okay, you're trying to separate out. Okay, one point which doesn't come in the. Okay. Light cone of like let's say you don't want x2 to come in the light cone of one of the, let's say x3. That's why you get the second one and all that.
Yeah.
Why are you calling this time ordering? Because 1, 3, and 4 are always in the same time space, right?
Yeah. So I'm calling because theta 2 I put it at the left. So this is my so whatever is highest. It doesn't matter. Because these are at the same time, I can write whatever it is. Yeah. But because this is at highest time, I put it at the left. I call it as declare it as a time order. That's my notice.
So then there is the second one. Okay.
This is not time order.
Okay.
This is not for time order. This is time order.
Okay.
This is some order.
What operation are you calling here?
What operation am I calling? Sorry. Oh, how do I go from here to here? Here to here?
No, that's fine. Okay, that's because you don't want theta 2 to be in the light cone of theta 3. Okay, that's why you get the second one. That's fine. Okay. But I thought you were calling this time ordering.
No, it's just a random order. You've got 4 guys. You've got lots of possible orderings. Most of them would have rings.
2 to the 4 means 16 ordering, 16 different choices that you can make. So
all 16 are presented by these.
Yeah, so you can always find out path. Either 16 or 8 you can find. So okay, so now suppose you want to. So what will be in a 4-point function? So till now, if you have not followed all you need to know was that there is a difference between 4-point function and a 2-point function. Difference is that in the case of 4-point function, you have multiple branch cuts. So, for example, like this, and then if you cross one of the branch cuts, it's not clear that the other branch cuts will remain at the same position. How do I see it here? Suppose I have this diagram. So this is a branch cut, and suppose I'm crossing like this. I'm going like this. So this is a branch cut. This is also another branch cut. It's no longer clear that this branch cut will remain at the same position. It can shift. So it can shift, say, this direction or maybe this direction. Then, if causality, if it has to be causal, this branch cut cannot shift here, because then you will get. So let's restart. So here, let's say I have theta 2 here, this point, where there is so this is say
you get a non-zero commutator between theta 2 and theta 3.
That's right.
Inside this one.
Yeah, exactly. Inside the 4-point function. So if you see,
when it's not, space
even when it is space like separated. So this is going to be important point. So see, I got it. Sandeep got it. But other people, if any questions.
No, explain it, please. I'm not sure I understand.
Okay. So suppose I put a operator theta 2 here, theta 3 here, this is theta 1. So this operator is space-like separated compared to this operator. So clearly the commutators will be 0. But suppose I'm reaching here from here. Suppose I'm reaching here from here. And because there is a branch cut I'm crossing, suppose this shifts, this suppose shifts somewhere here. Then if I am reaching here, then maybe it so happens that this theta 2 and theta 3 are no longer space-like separated. They become in the correlation function because I'm crossing a branch cut. So I'll get a non-trivial commutator. So this is going to give me inside the correlation function non-trivial commutator, and clearly this is going to violate the causality. So all I want is that this cannot shift here. If causality has to be there, it can shift along these sides. Okay.
But brain also there will be like it won't be space-like separated like
Where?
So you should be that.
It will still be space-like separated.
Okay.
I mean space-like in the sense I won't get any commutator. The basic point is that I don't want to compute exact commutator. All I want to show is that if it is 0 or non-zero, that will be my causality criteria.
Just one quick remedial question. Suppose you had drawn your waveform was not infinity.
Yeah.
And you went through all cuts.
Going to all cuts, okay.
Then you would get the anti-time ordered. Then you would get the anti-time ordered, right? This would be all the way down.
Yeah.
And there should be some symmetry between this and that.
Oh, you see time order and
anti-time order somehow should be more or less. I was just wondering whether that told you something about how cuts shift. Whether there's some constraint. It's a big question.
Can you understand this in 2-point function? So for example, in the 2-point function, I have, okay, so I have basically this. And so other thing is y2, y2. So given this, I know how to go here. Right. Because my branch cuts are known.
So I suppose with the 2-point function, I was saying that it's clear that both the 2-point function and the anti-2-point function start at the causal law. I mean, both the time order and the anti-time order can only have singularities from the causal law. With the 2-point function, this is a trivial.
Oh, I see.
So what I was asking was here, when you approach the first guy,
I see.
so you're approaching from time order, you knew that you would not be able to violate causality.
I see.
So I was just wondering when you went through.
Oh, you're asking in quantum field theory, do I know something like time order and anti-time order must have the same singularity structure?
Yeah, something like that must be true, right? Because there's time reversal invariance.
Time reversal invariance.
Then the direction which of the sheets you start from?
But maybe.
Yeah, what I was thinking was that he was talking about the shifting of the location of these branch cuts. So I was thinking that if you go through all but one, you should know that it cannot have shifted. Just because you know that it became. Is that right?
Then maybe what will happen here is that suppose I don't know the scenario. Suppose I cross this, it shifts.
Yes.
Suppose I didn't cross this, it might shift back.
Yeah.
That may be very interesting, but not
I mean, I don't know. But of course, there are shifts depending on the path taken, right?
Yeah.
You're just saying, so it's not true that if you follow one path and get somewhere, another path and get somewhere, the shifts are the same.
No, what I was saying was that if you're doing time ordered, you can only get shifts when you go through one and then another. Okay? So there should be an analogous statement for anti-time order. So the first time you do a time flip, that has to be at the right one. But first now gets interchanged with last.
Yeah.
So it seems to me that the last cut should be at the causal place. I may be saying this vaguely.
But your argument about time reversal symmetry seems to be, I have not thought, but maybe one way is the only thing I can see that it shifts back. That's the only way I can see.
Yeah.
For the 2-point function, but there is a difference in.
I'm not saying there's no difference. I'm just saying that the location should be at the causal place.
For the 2-point function,
Yeah.
Okay, so since nobody is watching there, I can. So first point was Euclidean quantum field theory, single valuedness. I have shown from starting from single valuedness how to go to the like multi-valued Lorentzian correlator and how to compute correlation function. But there are other properties like reflection positivity and crossing symmetry.
Sachin, it is being recorded, that particular.
Okay, so I'm told. So
this is a very beautiful one question which we can talk about later on, but just to ask, is there have you thought about the analogous and finite temperature field theory?
no. That can be.
Might be useful because the kind of things Logan is interesting.
Okay. Okay. So before going through the details of reflection positivity, which is very simple, I mean let me tell how is reflection positivity going to happen. So we have argued that this light cone cannot shift along this direction. If it shifts this direction, then the causality will be violated. So till now it's just a requirement, but not a requirement, but the observation that it cannot shift along this direction. But what prevents it from shifting along this direction? That's the reflection positivity. So reflection positivity will imply that it cannot shift along this direction. It can shift other direction. So actually there was some recent work by Mallasena, Jugolo, etc., where they show in 2 dimensions there is no shift, but in higher dimension they don't know whether there is a shift or not. So
no shift even without reflection positivity.
Sorry,
no shift. We go without assuming reflection.
I think the reflection possibility
is not required.
Maybe required. I may not know. I may not know the exact answer, but so the second player, which is reflection possibility, is going to play a role in ensuring the causality. Okay, and because I'm just the last role, but so this will just ensure the causality, but I'm not going to get any constant here. I want to get constant on my CFT. How do I get the constant? Then the last player comes. So this is crossing symmetry. So at the end, I'm going to discuss a little bit about the reflection possibility, which will ensure causality, and the second point would be to use crossing symmetry to show that that I get a non-trivial constant on my CFT. So this is what I'm going to. Okay.
You could have seen this in the 3-point function, right? Where you're considering 4-point functions.
I could have seen this in 3-point function. Which one I could have seen? I mean, like
your picture.
Yes. But I won't be able to imply the reflection positivity. I mean, I want to use reflection positivity. So 4-point function, you see, I have say psi theta theta psi. 4-point function will allow me to make it as theta psi, which will be positive. Interpret this as this. But actually, your comment is interesting. If I don't think I have time, but if I go to spinning operator, it turns out that the causality constant at the end turned out to be like theta theta t minus minus is positive, greater than 0. This is what it turned out for the spinning operator. Say here, GG. This 3-point function is positive. So, but we start with 4-point function, and then you can show that it effectively amounts to 3-point function.
Just following up on this question. In a conformal field theory, the analytic structure of the 3-point function is completely known.
No, yeah.
So you can just check whether this is happening, right? Just like analytically continuing. And presumably that just does not happen, because otherwise you'd have trouble.
You mean the shift?
Yeah, within this. Because how will it distinguish between reflection positive or not? It's just some analytic structure.
That's right.
So either you will show that conformal field theories are inconsistent, or the 3-point functions cannot have trouble, right?
That's right.
Perhaps with some bounds dimensions.
That's right.
Unitarity bounds dimensions.
Sorry, to show. So reflection causality is something you will have to ensure. Presumably, you will not define what it is.
But I'm saying within the 3-point function, you shouldn't need anything because you have the function. Let's say we've got 3 scalars. You know it's 1 over. You know the analytic structure. You can just do this continuation that he's talking about. Just the level of functions, and either this works or it doesn't. And all it can depend on are the 3 dimensions.
Yeah.
I mean, maybe it's something trivial like the coefficient is some sign or something.
Coefficient.
It's mean equal to 0 and all.
No, but it's just a function. It doesn't depend on the number multiplying the analytic function. It's just about the analytic function, which is completely determined in terms of delta 1, delta 2, and delta 3. Let's say all 3 are scalars.
Yeah.
So it might depend on some inequalities between delta 1, delta 2, and delta 3. Might depend on delta 1, delta 2, and delta 3 satisfying the unitarity. But it can't depend on anything else.
Because he's not a statement about coefficients.
No, because it's just the cuts, right, where the cuts are. So it's just the functional form. So I think 3-point functions within a conformal field theory, at the most within implying unitarity bounds, just have to work. It would be interesting with unitarity bound.
Yeah. I know. Okay, but it's a good point. Yeah.
But stated like that, it seems to be a condition that also involves coefficients.
Sorry?
But of course, in the
4-point function is more.
Yeah,
it's not fixed resonant.
Yeah, 4-point function problem is I do not know the full answer.
Yeah.
So I have to rely on all these things. But as I say, a 3-point function is known, I can just check. So,
but I mean, something simple like if the 3-point function is imaginary, I don't know. I don't know how complex computation. I mean, positive norms seem to be distinct also.
But that's another criterion. His criterion is just whether the location of the cut shifts this way or that.
Oh, I see. No, I was thinking that there seems to be. I mean, is this entirely equivalent to the movement of coefficient? No, it doesn't have anything to do with norms being defined.
If what I'm saying, if this is ensured, then causality is ensured. That's what I'm saying.
Then his cut shifting is ensured. Like causality just means the cut shifts up.
Cut shifts up.
So he's going to show us in 4-point functions that if this is true, then it will always shift up. But in 3-point functions, it just either shifts up or does not.
What if I try to define a conformal field theory where the 2-point function was negative? But some cut structure is whatever it is. Would it still be reflection positive? I'm just asking, would it meet your norm conditions?
If it is, you're saying already negative.
Yeah. Maybe there's some dumb thing. Maybe you always assume all that is true. Okay, I was just trying to.
It will not be his norm condition, but it will be his cut conditions.
His cut conditions.
Because the cut conditions are just.
And maybe so when you say reflection positivity, you mean all the obvious norm conditions are met anyway.
I think norm conditions will follow from reflection. Right?
Which one is it?
Norm positive will follow from reflection. But sorry, just to be clear, I'm just saying that the question of whether its cut can be violated, independent of reflection positivity. So 3-point function just has to work. Modulo. Yeah. And then there are many other things you want to be able to.
But it may give
the unitarity bounds. That would be very interesting.
Yeah. Okay, so I'll now briefly. So till now, everything we talked is general QFT, no CFT as well. But now I'm going to work for a particular CFT, in a CFT, not particular CFT, but in a CFT. And
so Sachin, is the 4-point function condition that you told us for a general QFT, right?
Yeah. No. But now I want to show causality, etc., etc.
So let me just ask you, because from this point onwards, right, you cannot turn it into some condition for an experiment, so it's very difficult.
Actually, the way I'm going to go is applicable for CFT, but if you have a QFT, similar thing may be applicable, and we do not know at this moment, but some people are working on this. I will get a condition at the end. You will see that it's not exactly the unitarity positive. I mean, like imaginary part of this is positive, but similar to that. Okay, so this is a 4-point function I'm interested in. Psi and thetas are different. Let me choose this. And so suppose I set the positions to be the same as earlier, that this is at 0, 0, 0, 0. This is at t2, y2. This is at 0, 1. And this is at infinity. What a special coordinate to be infinity. Okay. Then CFT says that, like in the CFT, the way we can express this in terms of the cross ratios. The cross ratios are defined as this: x1 2 square, x2 4 square, x1 2 square, x2 4 square. x1 4 square, x2 3 square, x1 3 square. Okay, so these are my conformal cross ratios, and this is a variable that you will be working with, and this can in general be written as say I have, for example, theta 1, theta 2, theta 3, theta 4. So this can be written as, sorry, it just just give me 2 minutes. So I'll just write this and I'll come back to it. So I'm just writing in terms of so these are the conformal cross ratios, and here are some prefactors that arise in a CFT. So I'll just write theta 1, theta 2, theta 3, theta 4. This is in general given by this, and here I've brought theta 1 close to theta 2 and theta 3 close to theta 4. So this is in general the structure. Okay. Now, for the case of this example, where I have this x1 is at 0, this is at t2, y2, 0, 1, psi infinity.
Sorry, Sachin, stupid question, but the first 2 terms were basically 2-point functions.
Yeah.
Oh, and I see, but they would have been 2-point functions had delta 1 been equal to delta 2. That's why it's delta. Thank you. Yeah.
Okay. Yeah. So, for this configuration,
So had you written the other channel where the thetas were brought together, the psis were brought together, then all you would have had would be the first 2.
first.
Yeah, because delta 1 2 would be 0.
Yeah, exactly.
Actually, what is delta 1?
I'm just saying, say, theta 1, theta 2, theta 3, theta 4. Delta 1, 2 is delta 1 minus delta 2. Okay, so at this point I'm not going to talk about the other channel. I'm just going to talk about the only one channel where I have brought psi and theta and psi together. Because I'm going to focus on the diffusion probability. So let me now specialize to the case where already you know, I'm like theta 1 is psi, theta 2 is theta, and these are the particular positions. And then you can compute the conformal cross ratios, and what you find out is And this full 4-point function then reduces to
in your notation, tau 2 is real and serious, right?
yeah. Sorry. So here is just a notation. This is just a functional GZ1. So these are conference blocks. Delta P's are the primary. So what I'm doing is that I have psi theta. So this is the conformal primary, and this contains all the descendants here. So this
in Euclidean space, bringing your two operators together is doing what to Z? Bringing 1 and 2 together.
J to 0. Exactly. So I can have as you say, so I can do a series expansion here, and what I'm going to get is that this will be some factor times some AH bar notice that so now next step is what I will do is that using reflection positivity, all I'm going to argue is that this is positive. This coefficients are. Okay.
Roughly, it's because they're 3-point function squares, right?
Yeah. That's right. They're roughly because those are 3-point functions square. That's right.
So reflection positivity in particular implies that 3-point functions are real.
3-point functions are real.
Let's go to the CI.
That plus some combination of norms, right? So actually one of those indices is raised.
Yes, strictly speaking.
Oh, which is sorry.
I mean it's the 3-point function, but then you have a 2-point function inverse propagator or something.
Yeah.
So it's that combination that is real.
Yeah.
That's what was that connects with our discussion with the norms.
Okay, so
what's this last clarity?
so I'm just doing a series expansion as you have pointed out that if I bring these two close together, all I'm doing is that taking z bar to 0.
Yeah.
So this is a series expansion. Okay. And this is valid up to 0 to 1.
The operator product.
Operator production. Now, what I'm claiming is that all the reflection possibility is going to do is that this is going to set AH bar is positive. And
So this is implied by reflection positivity, but you're also saying that nothing else is implied by reflection. There's no other constraint or
no.
just that.
And just to understand, reflection positivity will simply be a statement of how your cuts will move. I thought reflection positivity is an intrinsically Euclidean concept.
Yeah. Now I'm going to show. Now I'm going to show.
How does it define reflection?
Now I'm going to show that this fact that this is greater than 0, how it ensures that the cut. I mean, how the cut moves around. How this is going to ensure.
So your definition of reflection positivity is that all the coefficients are greater than 0.
No. Okay. So let me define a state, which I have written somewhere. Let me find out. Just give me a second. Okay. So yeah. Let me define a state, which is like. Sorry, that's in
When you're doing a series expansion of the conformal.
Sorry. So let me define a state at psi at 0, and then acting on vacuum, and then I have theta at some, let's say, some point, say W, and then I have some function which will define, say, function of W. So this is my, say, I define this as a state. Okay. So this state, all I'm just claiming is, yeah. So in the plane, I have R1, so R1 theta 1 and psi at u. Okay. This is what I define as my state. So all I'm doing is that I'm putting my CFT, suppose a two-dimensional plane, and I'm thinking in the radial quantization, and I have inserted. So, and then let me define a reflection reflected compared to that unit disk a state which is defined with respect.
I actually haven't understood. What's f? What's the current side?
So if is some function that I will pick up, that I'll pick.
Okay.
And theta is the operator.
Operator, which is just one operator.
Yeah.
Could be many.
Could be many. But I'm just considering 4-point function.
Yes.
So and the psi is the other operator.
Yeah. So two operators.
Yeah. Two operators. So the conjugate state that I'm going to define is so.
You chose it to put psi at 0, but you could do something more.
I could do more general.
And you just invert both.
Yeah. I can just invert both of them. But yeah. So. dr1, so some 0 to 1 maybe, and d theta 1, 0 to 2. The conjugate state will be some dr2, 0, psi at infinity, and then I have 0 to 1 again, 0 to 2 pi, d theta 2, and then f star up to theta 2. O, the reflected with respect to the this.
So 1 by R2
yeah.
and minus 2.
Yeah, exactly. Minus. Now, this is exactly so. Just one intuitive picture is that I put, say, for example, theta here and theta here with respect to a time plane. So I define a state up to here. I define a state up to here in the path integral sense, and then their inner product I just demand that to be positive. So all I'm going to demand is that this is greater than 0.
So in the end, this is a statement just about correlators, right?
This is just a statement of the correlator.
So and just in terms of correlator, you have one guy at infinity, one guy at 0.
Yeah.
These two guys smeared in a reflected way.
Yeah.
With a complex conjugate coefficients.
Yeah.
And that has to be greater than equal to 0.
That is greater than equal to 0. And it's a bit of algebra, but just believe me that if you choose appropriate function f, you can show that this AH is greater than 0. It follows from this.
Why are you smearing this up?
Because if you don't smear, you will get a summation over AH bar. You want to pick up some particular AH bar and show that this is positive.
You can think of this as just the state operator.
Yeah.
This guy produces some state.
Yeah.
And you want to show that the basis states have positive norm. So if every state has positive norm, it implies the basis states have positive norm. And this F is just giving you an arbitrary linear combination of the basis states.
Yeah. So yeah.
Okay, you invert. Okay, you take 1 by R2 here. Why don't you take 1 by R2 in F star?
It's some function. It's just some function. Whatever this function is, I just define it as a complex.
Okay.
Suppose I give you a function.
Yeah, but if you think in the part integral sense, okay, like you're integrating from let's say 0 origin to one unit sphere, and then if you're doing part integral from for the bra, you're integrating from infinity. So you integrate it from infinity to 1. Okay. But that's why you get 1 by R. Right?
Yeah, that's right.
So, but why aren't you taking F star to have 1 by R?
F is a function of who's defined where R goes from 0 to 1. So F star at R equals 10 makes no sense. Right? F was defined by the original state, it was only R goes to 0. What you're saying is you want to put the same insertion here as at the reflected. So you have to put the same coefficient R2. Yeah.
Sorry, I have another question. So this H bar greater than 0. It doesn't just tell you that the 3-point function coefficients are greater than 0. It also tells you that whatever coefficients that pick up in the series expansion of the conformal block, each of them should also be greater than 0. Right? That's a stronger constraint that you're putting on conformal blocks themselves. Is that not correct? Because H bar are the two C's times whatever term you pick up in the expansion.
That's right.
So, right?
Yeah. So H bars will be a bit determined in terms of this, but I'll have more things there. That has to be positive. That has to be. That at the end may be related to this also. I mean, this is related to this as well.
I think the condition you're mentioning has to be true in any consistent. But the conformal blocks have to be an expansion in positive conditions. I believe if you take conformal blocks between equal, just because otherwise it conflicts unitarity. Like unitarity requires that all 3-point functions are positive, not just those are primaries. And so, as you said, for that to be true, it had better be that the conformal blocks automatically satisfy this criteria. At least when you take O1, O2, O1, O2. And I think it's a true statement, right?
Yeah. So here you see, I'm not to make, so this at the end will not be primary state. This will be primary plus all the descendant at the center. You see. So this is okay. So all I have achieved by reflection positivity, which I have not shown the details, but you can see details in my paper, in our paper, that these are positive. So now, how does it help? So you remember what we wanted to show was that all we wanted to show was that reflection possibility ensures causality, which means that the light cone can shift only along some direction, not in the other direction. So this is what I am going to show now. Okay, so this, let me define this to be detailed bar, 4-point constant. Now, you see that although I required reflection positive point to ensure that these are positive, but now I can go away from reflection positive point and choose my points. But because I have already argued that these are positive, I can still use that. Okay? So the configuration that I am going to use is again psi 0, theta at tau 2 y2, and theta at 0, 1, and psi at infinity. This is the configuration again I am going to use for the computation. And if I draw the light cones, I already had drawn earlier. Somewhere here. So, and theta 2 is here. This is theta 1, this is theta 3. Okay? Now, what I want to do is I want to reach here. Great thing about this configuration is that the g and g bar variable which appears here is this is a z, and this is z bar, and this is z. Let me make sure I am just writing correctly. That this is z and this is z bar. Yeah.
Could you rewrite what you said was in terms of y and tau? Just
y2 is tau 2
with I if tau 2 is. Now you've got to convention that tau 2 is real.
Yeah. So now, how do I go here? So one way is to follow the path. Take g around this value here. Because, so this is z and this is z bar. So this is positive z and this is negative z. So I go from g to g bar. Now you see, if I say z to minus z, I get a extra factor of h bar minus 1 to the power, say h z to the h, z bar to the power n. Now because this is a phase factor or a minus sign, this is always less than this. Why this is important? This is important because this is our time order stuff where I did nothing to go from one to the other place, which was just the analytic contribution from one to the other place. So the light cone was always here for this stuff. But once I'm doing this reflection, I'm really crossing the branch cut. Then the question was whether this shifts along this or this. All I'm saying is that the value of this decreases. So clearly, if this was a singularity, if I go follow this path, the singularity it shows that C is the singularity to be shifted.
And you're using the fact that the radius of convergence of this expansion, it's where it fails is the point of location of this.
Yeah, exactly.
You're saying it's clear that this converges, that converges better.
So because this converges, this is going to converge. And this has small value, so it has to have. The point where it converges, as he has pointed out, more better way, is that the point where it fails to converge is this point, because it is the singularity. But because it picks up a phase factor, the singularity cannot shift along this direction. It has to shift along this direction. Okay. So all I have been able to show you and this ensures the causality. So this is a simple example. So I have used two facts, single valuedness and reflection positivity. I have not yet used the crossing symmetry. So in maybe 5 minutes I am going to talk about reflection positivity. Last crossing symmetry.
I'm sorry, how do you see this spaceship as a shift in that light?
Okay. Just give me a minute. Sorry, I'll just get Okay, so the question that was asked is how do I see that this factor is going to shift the phase here, not here. So this is the question asked. Let us. So maybe I'll answer the way Siraj said. The way Siraj said is that you see. So I have this is Lorentzian picture, θ1, θ2, θ3. These pictures are where the these are the lines where θ2 and θ3 are coincident. So there is a singularity here. So the radius of convergence of the series is up to here. It has a singularity here. Okay. Now this expansion was valid also here. First expansion, I just went. So there was two pictures. You remember. So the picture was like this, and the second picture was I was crossing like this. There were other. So this picture is basically I'm crossing this by picking up this phase. I'm crossing an analog of this. So you get an extra factor, and you reach again at the same point. But what you see is that the value of the cohesion function decreases if you reach it. If the value decreases. So let's consider a path here and then go here. Okay. If you are here, if you are not crossing the branch, if you are following this path, you are not crossing anything. So this is the expansion. Clearly, the singularity is not going to shift, and the singularity is here as you approach this. But if you take this, which is this, then you see that because this value decreases, so singularity has to shift along this. Because had it been, how would have? Because it is saying less value. So I have said okay. I will not be clear about that.
Now let me just restate that. That object is always less than equal to that object because we can take moments. Yeah. So place where that series converges, this has to converge. And so, but we knew that series converged everywhere that it was space-like separated. Therefore, that converges everywhere when it's space-like separated. Therefore, you could not have crossed a singularity.
Okay, sorry, you were next.
Why did you say that z bar is greater than 0?
Sorry?
The inverse is right?
Yeah. No, so G is less than 0 to 1, 0 to minus 1. Which I have crossed here. Here it was, as you said, 0 to 1. Okay, so now the last ingredient is the crossing symmetry, and this is what I am going to now use to constrain the CFT. Okay. So
far you've shown us that if you've got a CFT and all 3-point functions are real, then causality is automatic. Within 4-point functions.
Within the 4-point
at least.
Yeah. Okay. So now I want to.
And therefore, if you have a CFT that violates causality, there must be at least one non-real thing.
Non-real. Okay. So you remember. So let me just say again what I mean. So psi theta theta psi. Okay. What did I use? I use. Let me call it H channel, which other people use some other name, but. Here I use psi and theta close together, psi and theta close together. It's like a state. Psi theta, psi theta. Okay? They use that. Okay, so this is positive. This is what I have used till now. Okay? But I have Euclidean permutation invariance tells me that this should be same as where I bring close together theta theta and psi psi. And there is no, these are not like any state, because this is not, I don't have any statement like theta, theta, psi, psi. I don't know. I mean, like, I cannot explain. This is clearly not, this is not a norm. So I cannot say. So I have to do something. This is, if I draw, then I have psi, psi, theta, theta. So intermediate things that are extent like identity operators, stress tensor, and all the stuffs. Okay. Now, this is again very complicated. But what I am going to do is to take some particular limit where I have a handle of this question. That particular limit is called the light cone limit.
So just to understand what you're doing, Sachin. So you're saying that if in the previous case you chose some particular identities of operators for 1, 2, 3, 4. Yeah. And the one was, let's say, can you show what the choices were again?
1, 2, 3, 4.
3, 4. Excellent. Okay, now you're going to choose the other kind of vector.
Yeah.
Both psi psi and theta.
Yeah.
And you're going to check, you got to prove causality also.
No, causality already been proved.
Already been proved.
So because of the duality, if I even go to the T channel, these things are always ensured. So I don't need to think about causality. Now what I want to do is to actually get the constant. I want to use whatever I have done to get some constants. Okay. Just look at this once more. So I'll call it as a first set answer.
Sorry, constraints or what?
And 3-point functions. First set, and this is called second set. Because I have crossed the branch factor. And the property that is important is that the second sheet answer is always less than the first sheet answer. Okay? Because of this space vectors. So in this channel, I have identity or stress tensor. These are the operators which are going to get exchanged. Let me take a light cone limit, which is basically, in this case, basically you are approaching this light cone, keeping G fixed. So you are approaching Z bar goes to 1, Z fixed. In this limit, what you can show is that this 4-point function is organized in terms of the twist expansion. So I will have contribution from identity, I will have contribution from the stress tensor. I don't need to, all the other higher, other thing which have higher twist is going to be suppressed. And this is my assumption, is that I have stress tensor as the lowest twist. These are my assumptions. Suppose I work in this assumption, that stress tensor is my lowest twist. So, I have to use one more complication. I have to introduce one more complication. Otherwise, I will not get any constant. So till now, the picture that I drew was only one point was time-line separated compared to the other. But in order to get constant, I need to do the two of the operators. So one of the operators is time-line separated compared to the two others. Okay. So how am I going to ensure? I'm going to ensure two operators sitting very close by together, and so very close. So they will have maybe identical line, and theta 2 sitting here, and one of the theta sitting here, sine. This is my picture. These are called soft wave states that I chose. Basically, it was motivated from the ADS safety picture, but it is very useful. You know, if I go to spinning operator, these are very useful to impose recursion positivity, etc. Those become automatic. You can work with general operator, but those will be, like general insertion, general operator, those will be complicated. But okay, so what's the physics point is that, so I consider this situation where one will be like time-line separated compared to the two. Okay. Now, this is like Minkowski space. And
so the difference from before is that this theta is no longer at 0, at t equals 0.
Yeah. So here, so suppose I start from here and go here. Again, I have to, in this configuration, again I have to show that this shifts this way rather than this way. It's a bit more complicated, but exactly same. I'm not going to show. But if I follow this path, that I cross this, in the G bar plane, what it happens is that it happens is I have singularity at G is equal to 0. So this, sorry, I may not be saying this very clearly, but so this G bar psi theta 1 psi infinity. So what you can do is that any configuration can always map to this configuration in a shape. So the branch paths are here. For this configuration, following this path, you can show is that you are going from, like this. Sorry, these are some details, but what will be important is that you can show based on this distribution positivity that this is these functions, both G, let me call G1 first shift and the second shift, both are analytic here in some region. Okay. Let me. Sorry, these are some details I don't have. Okay, so I'll just redraw this picture here. This is my choice of some semicircle, and what I claim is that here everything is analytic. So what I'll do is that G minus, say G1 minus G2 integrated over this is 0.
I missed actually. What is G1, what is G2?
So G1 is the first seed answer, G2 is the second seed answer.
And what is the special point?
This point is this point. G is equal to 1.
And sorry, can you show us that special point in that diagram? Is that possible?
No, it's this way. It will be okay. So in this diagram, roughly, I mean, this is space-like picture, and G is a little complicated here compared to earlier cases because of the insertions are very different. But what you can think is that in this diagram, this is somewhere here, and here we have used analytic properties to claim that here everything is analytic.
But there's no special point there, right?
Where
the branch path starts.
That will be. So this picture and this picture is not totally equivalent, but this is just G is equal to 1. Okay. And maybe related to somewhere here, somewhere here.
There's no physical way of saying what that special point is? Or it's just a map? I mean, it's not where to light codes cut or something.
This has to be this. This has to be this.
So on that light code, but where on that light code?
Oh, where on that light code? I do not have a very good.
Okay.
Thinking about that. Actually, this coordinates are a bit complicated. And
yeah.
G and this becomes bit. maybe I should have drawn. But all I wanted to emphasize is that this is just 0. Now, okay, so interesting point. I know I should be more careful, but this interesting point is that along this line, it so happens that z bar goes to 1 and z is fixed. And along this line, both g and g bar simultaneously goes to 1. Just some little detail. So this thing is light cone limit, and this thing is called something called Regge limit. In this limit, here I know the results because I know the expansion in terms of block expansion, that I have identity contribution and the stress energy contribution. But here nothing is known. Only thing that I require here is that first seed answer is greater than the second seed answer. So if I rewrite this, so this is going to be, if I rewrite this thing, this is on the real line, will be related to the integration along the arc. Okay. Okay. So at the end, what you are going to get, I'll define what is lambda is, and because first seed answer is always greater than second seed answer, you get lambda greater than 0. What is lambda? I'm sorry. So this one will be for. So lambda is just basically the 3-point coupling that you have: C psi side T, C theta theta T. That all we have claimed that this is greater than. This is pretty good.
What about the contribution along this branch cut? Like, you can't say anything. Like, what was the comment about that? I mean, there is a branch cut along this. So, what was the comment about this? Like, you are integrating it over this path.
Yeah.
So, what was it? Sorry, what was it?
Maybe is simply with the branch.
I think this question was what about the flat part of the grid?
Oh, the flat part of the contour is this. This is along the real line.
So the lambda comes from the curved part.
Yeah, lambda comes from. So this is the light cone part of it, and this is the Regge part of it. This part was maybe a little more technical, but
I see. So the left part you don't know anything, but you know that there's an inequality.
Yeah, I know the inequality.
And the right part you can just evaluate.
I can just evaluate.
And that right part gives you this thing, and therefore you can use it.
Yeah.
Sorry, sir. What was this? Like, I didn't get it. Like, what do you say about along the branch cut, like the flat part?
The flat part, you don't know anything, but you do know that G1 is greater than G2.
Okay.
So that integral over that flat part, you don't know what it is, but it's greater than G2. The integral over the semicircle is given by this light cone expansion, and so that is determined by basically the identity exchange and stress tensor exchange. Identity exchange is trivial, so it's determined basically by stress tensor exchange.
Yeah.
So the circle part gives you this C, psi psi T, C theta. So you've got an equation where something is known in terms of 3-point functions, the other thing is unknown but is greater than 0. So you get an inequality.
Actually, okay. So what you can do, just I can show you later. But this first seed and the second seed here, how lambda comes? There is a log piece that appears. Okay, in the expansion of the if I have stress tensor extent, you take that log. I mean, like you go around g is equal to 0. So that picks up a phase factor. Log z will give a factor. That is why you are going to get this, and that's the branch cut basically. Okay, so what you get is for this, but you can immediately say that this is trivial because C psi psi T.
So is it somehow related to the fact that anomalous dimensions impact
Negative or positive has a particular sign
and are determined by these things?
Yeah. I mean, analogous dimension case also they do the same. They use the light cone expansion, and the other case and the external expansion they get positivity.
What I was thinking was that this is the cut bit the discontinuity is, as you explained to us, determined by your h's, and these h's pick up some anomalous dimension.
Yeah.
And so the discontinuity gets a contribution from the
Yeah. Okay, so actually it so happens, maybe I should not tell this, but for the scalar case, it so happens that this is related to delta theta, delta psi by some c squared or some c, okay? Which you can say for a unitary CFT is automatic, that this is greater than 0. This has to be greater than 0. So in that way, I don't get any non-trivial bound.
Where does this relation come from?
Some conformal word identity.
The word identity using the fact that T is special.
Yeah. Now, just in 5 minutes, I'm going to emphasize that nevertheless this is useful because suppose you consider T psi or J psi or maybe some higher spin. Then these are constant on the 3-point function. What you can show that in a CFT, say in 4 dimension or in high dimension also, you can write down this TTT. I'm just giving an example of this. Okay, so it has a exchange in the T channel from the. So the picture is the following. The argument of the diffusion positivity is little bit more involved, but everything is identical. So there is an exchange of stress tensor. You can. So this is the 3-point function. This is important. So I can write it down as TTT of free scalar, NF of free fermion plus NP of free fermion, free vector. Okay. Basically, you write down Lagrangian for free scalar, free fermion, and the free vector. It's a in 4 dimension and compute this 3-point function. This has been done in PET 2 and Osborne PET 2, so you can see. And actually, you can go to any dimension and you get constant. Sorry, just give me a minute. I wrote down constant somewhere. Sorry, I wrote it somewhere. I forgot where I wrote. Yeah. Okay. So you can go to any dimension and you can show this is positive. D minus 2 squared NS NF greater than 0. D NS 4D NF 128 ND. So these are non-trivial constraints. Okay. So in general, if I don't impose causality, so this says that all possible values of NF, NS, and NB gives you a consistent quantum CFT. But causality demands that no, not all the values are allowed, but these, the CFTs which satisfy these constants are only allowed. Okay, so this is some non-trivial constant that we get. There is a way to improve, but maybe I'll talk you in.
And you're saying it's causality because you crucially use G1 greater than G2.
Yeah.
That's which ensures causality.
Yeah.
Okay, questions, comments?
Can you make a statement like if you have some, not like higher point function, k-point function, then in every possible branch cut that you cross in any possible way, every time it should shift in the direction. It should be like that, right? For any that ordering that you define.
And it should shift in a way where it should not violate causality.
Yeah.
So it may be the direction you said that it has to shift in a particular way.
Well, let me follow up on that. Will that be automatic from what you said, or you'll keep getting more and more constraints?
If I have higher point function.
I mean to say, like, is there some induction kind of thing that you can think of?
One thing I know, I may not be able to give you argument right now, but any higher point function in a CFT, more than 4-point function, can be actually written in terms of 4-point function. So I'm not totally sure whether those are going to give you something extra. But I mean, flavor of the argument will be same if I use that, but maybe more complicated.
I think there will be more cross ratios that you have to consider, and that could involve more and more complex planes on which you can do this continuation. So may give you more constraints.
But it will be ultimately constant on the 3-point function.
Yeah, but
you are asking between. So the question, let me understand the question. Suppose I consider all possible external operators in 4-point function, and I get some constant. Question is, if I consider all possible operators in the higher point function, do I get more constant or not? Maybe not. I'm not totally sure, but maybe not.
No, but let's say, okay, you have been considering, let's say, your AN or, okay, I forgot what you call it, AHH bar or something, okay?
Yeah.
You are considering AHH bar to be positive, okay. But if you consider a Hartman function, maybe you can put a upper bound in it.
I don't know. It's complicated, but might be interesting. I do not. Seriously, you have a comment about that?
No, my guess would be what you said, that it should be automatic. But maybe it may be automatic in principle, but not in practice.
Not in practice.
Because often you're actually just expanding.
Yeah.
Let's say you do like a light code expansion.
Yeah.
It may be that all orders works in 4-point functions. All orders will work there. Maybe a better way to pull out that information. Other questions, comments?